Bismillah ar-Rahman ar-Rahim. So today's the first topic is that we would be discussing a table about the damping ratio, that is zeta. In last lectures we discussed about the damping. Damping actually represents the energy losses or the energy which is dissipating out of the vibratory system. So we are modeling that energy as damping. And then we discussed the damping ratio, which is actually the ratio of the actual damping in the system to the critical damping. And it is denoted by zeta. In this table, you could see the damping ratio for few vibratory systems and also for some materials. So in the material, as we discussed that there would be material damping. So as you could see that in the first row, we have the damping ratio for automobile shock absorbers, which is between 0.1 to 0.5. So you could see that in automobile, the suspension system is actually under damped system. The damping ratio is less than 1. So in uh, automobile, the vibration would be under damped vibration, under damped forced vibration. Forced vibration, we would actually study the forced vibration in the coming lecture. Next is the damping ratio for rubber. It is 0.04. This is the material damping ratio. Riveted steel structures. So again, the damping ratio for a system, 0.03. Similarly, concrete has a damping ratio of 0.02, wood 0.003, cold rolled steel 0.0006, cold rolled aluminium 0.0002, and phosphorus bronze 0.00007. So here you could see that the system would have the damping ratio, and real systems would be damped system. They are actually damped system. There is damping. But if the damping is small, then in that case we could ignore the damping for the sake of simplicity of the modeling. What would be the advantage? The advantage would be a simple equation of motion, a simple and a simple derivation, and a simple analysis. But the disadvantage would be error in your computation. But if the damping ratio is not is the damping ratio is considerable and it is not ignorable, and in that case, if you ignore the damping ratio, then actually the error in your computation and analysis would be tremendous, and it would not make any sense when you would be when you would be conducting the experiments, and in order to find the response of the system or the behavior of the system or the characteristic of the system under vibration. So there are a number of methods by which we could find the damping in the system or the damping ratios. One of the method is the logarithmic decrement. This method is actually used to measure the damping ratio in underdamped systems. And this is an experimental method. This is an experimental method. So if we have the experimental plot of the response of the system, then we could use that plot, and from that plot very easily we could find out the damping ratio, and then we could calculate the actual damping in the system. Here you could see, let's say this is the actual plot of the system, the time response. This is known as the time response. The displacement along the vertical axis, we have the displacement, whereas along the horizontal axis we have time. So this is the displacement time plot, also known as response of the system, or time response of the system. This is the time response of the system, because along the horizontal you could see that we have plotted the time. So if we have this plot, which we actually got, let's say if we have got this experimentally, then from that we could actually find out the damping ratio. But for that, again, we would be doing some modeling. We have to develop, or we have to derive such an equation which we could use to calculate or compute the damping ratio. So let's say this is the experimental plot. Here you see that here the time is 0 and the initial displacement is this, and let's say the initial displacement is denoted by capital X. Initial displacement means that when time is equal to 0, how much is displacement. And you could see that as the time passes out, the displacement slowly and gradually decreases. In other words, the amplitude of the displacement is decreasing. So what does that mean? It means that our system has actually undergone through it has gone through a vibration. So our system is actually an underdamped system. And also you could see that with the passage of time, the amplitude of vibration has decreased, and after some time, the vibration would decay out. So what does that mean? It means that our system has actually subjected to free vibration or natural vibration. So in free vibration or natural, remember that in free vibration or natural vibration, if we subject an underdamped vibratory system to a disturbance, or it is subjected to a disturbance, or a disturbance is applied to it, so what would happen? It would vibrate, but with the passage of time, the amplitude of vibration would decrease and the vibration would decay out, and after some time there would be no vibration. The number of cycle it would pass, it actually depends upon the damping in the system. If the damping in the system is less, then we would have more cycles of vibration. But if the damping in the system is a little bit on the higher side, then in that case, the system would see less number of vibrations or number of cycles. So, in order to find out the or in order to develop a model with which we could find out the damping ratio. So let's say that we have already discussed that the mathematical model for this type of motion, we have already developed that is the response of an underdamped system. Response of an underdamped system is given by x of t is equal to exponential minus zeta omega nt times capital X sine omega dt plus phi, where exponential minus zeta omega and t is the exponential decay function. Actually, exponential decay function represents the exponential function with which the peaks are reducing. So the peaks are reducing actually with this exponential decaying function, which is given by exponential minus zeta omega n t. Capital X, as I already discussed with you, that it is the initial displacement. When time is equal to 0, what is the displacement? It is denoted by capital X. Omega d is the damped natural frequency of the system. And in the last lecture, we come up with this equation that omega d, which is the damped natural frequency of the system, it is equal to omega n, which is the undamped natural frequency of the system, under the root 1 minus zeta square, where zeta is the damping ratio, t is the time, and phi is the phase angle or initial phase. So generally, if we have an underdamped vibration and the system is actually passed through the free vibration or natural vibration, then the response of the system could be modeled by this equation. So we have already the model for the response of the system. So in this method, what we will do, you have to first we have to do the derivation. Let's say I'm taking this peak, and I'm noting, let's say, the time. This is I'm taking this as peak 1. So the amplitude at this is, let's say, x1, and the time at which this peak occur is t1. And then I have to consider a number of periods or number of cycles. I would choose a number of periods or number of cycles. Let's say n. So after n cycles, I'm taking I'm considering another peak, and this peak is actually xn plus 1 after n periods. So this is my point 1, where the amplitude is x1, and this is my point n plus 1, that is after n cycles, where the time is, the time from here up to here is t n plus 1, and the amplitude, let's say this amplitude is x n plus 1. Time t n plus 1 could be also written as t1, because the time up to here is t1 plus this time, the time between n periods, and the time between n periods is actually n tardy, where tardy is the time period. Tardy is the time period of the damped vibrations. So tardy is equal to 2 pi by omega d. So when we multiply this with n, I would get this time, the time between these two vertical lines. So if we add that time to t1, we would get time tn plus 1. So generally, the displacement x of t could be written as exponential minus zeta omega nt times x sine omega dt plus phi. We could write down this equation for amplitude x1 and also for amplitude xn plus 1. But here we have to plug time t1, that is amplitude after time t1. X1 is actually the amplitude after time t1. So using this model, just for t we have to put t1. So we would have exponential minus zeta omega n t1 times capital X sine omega d, or instead of t we would have t1 plus phi. Similarly, we could also write down the equation for the displacement x n plus 1. Here you have to just plug time t n plus 1. So x n plus 1 is equal to exponential minus zeta omega n t n plus 1 times x sine omega d times t n plus 1 plus phi. So we got the equations for two displacements, x1 and xn plus 1. So there are actually some common parameters, and actually what is the target? The target is actually somehow to find out an equation for zeta. So we don't want x and all those other quantities. So what we would be doing, if we divide this equation, that is the displacement at point 1 by the displacement at point n plus 1, then we would be in the position to have such an equation, or we would have a simple equation from where we would be in the position to find out or derive the equation for zeta. So dividing the displacement x1 by displacement xn plus 1, so we have that equation for x1 and this equation for xn plus 1. So here we have tn plus 1. As we discussed, tn plus 1 is equal to t1 plus n tar d, multiplying this on both sides by omega d, because here you see omega d. So multiplying this by omega d throughout, so we have omega d t1 plus and n is this one and tau d. So tau d is 2 pi by omega d. So we have multiplied with omega d, so that omega d would cancel with that one, and we would have plus 2 n pi. So if we put this in this in the argument of this sine function, so this sine function will be sine omega d t1 plus 2 n pi plus pi. In the sine function, if we actually have 2 n pi, if we are adding 2 n pi to the argument, then actually it would be equal to sine omega dt1 plus phi. It is just like sine alpha plus beta plus 2n pi is actually equal to sine alpha plus beta. So you could use that trigonometric equation. So meaning that this quantity sine omega d tn plus 1 plus phi is actually sine omega d t1 plus phi. So this quantity would actually cancel out with this quantity. Let's cancel it. So actually this quantity would cancel out with the top quality, and quantity x would cancel out with the other x. So x would cancel out with this x. Sine omega dt 1 plus phi would cancel out with sine omega dt n plus 1 plus phi. So at the end we would have x1 by x n plus 1 is equal to exponential minus zeta omega n t1 exponential minus zeta omega n t n plus 1. But remember that Tn plus 1 is actually T1 plus n star d. So here you could see that we have exponential minus zeta omega and T1 plus n star d. And then if we uh, open this parenthesis, then we would have exponential minus zeta omega n T1 times exponential minus n zeta omega n star d. So that quantity would cancel with this quantity. And here at the bottom we have exponential minus zeta and omega and tau d with minus sign. So it would actually go into the numerator, and in the numerator it would become exponential when it moves to the top. So exponential n zeta omega and tau d. And if you look here, tau d is 2 pi by omega d, and omega d is omega n under the root 1 minus zeta square. So we would have 2 pi by omega n under the root 1 minus zeta square. So x1 by xn plus 1 would become x1 by xn plus 1 is equal to exponential, and instead of tau d, we are putting tau for tau d, this one. So n zeta omega n 2 pi by omega n under the root 1 minus zeta square. So this omega n would cancel out with this omega n. And at the end we would have exponential n 2 pi zeta under the root 1 minus zeta square. So if you look here, what is the target? The target is somehow to find out the equation for zeta. And you could see that zeta here is in the power of an exponential function. How to bring this to the coefficient? The easy way is actually to take the natural log on both sides of the equation, because here we have e. So we have already come up or reached up to this equation. So taking natural log on with both sides, we would have natural log x1 by xn plus 1, and we would have, when we apply natural log here, so the power would become coefficient, and then we would have natural log of e, and the natural log of e is actually 1. Natural log of e is actually 1, so we got this equation. And this equation is actually known as logarithmic decrement. Why it is known as logarithmic decrement? Because here we have applied logarithmic function. We have taken the log of the equation. We have taken the natural log of the equation. You could see that the equation on this side is in log form. And decrement, because we are dealing with underdamped free vibration, and the amplitude is decreasing with time. So this ratio is actually decrement. So this method is known as the logarithmic decrement. We could also bring this n on the other side of the equation. So we would have 1 over n natural log x1 by x n plus 1 is equal to 2 pi zeta under the root 1 minus zeta square. So if you look on this side of the equation, we have zeta. And on this side of the equation, we have parameters which we could measure from the experimental plot. And we have to choose the number of cycles. X1, you have to choose actually the amplitude or the point for the amplitude, 0.1 for the amplitude. And you have to choose actually the number of cycles. So you could also measure the amplitude at the other peak, which would come after n plus 1 cycles. So meaning that we would know x1, we would know xn plus 1 and n. We could measure all these. So this side of the equation would be known. The only unknown in this side of the equation is zeta. So using this equation very easily, very easily we could actually determine zeta, that is the damping ratio for the vibratory system. There is some actually, we could write down the equation in more simple form. In case if we know before in hand that zeta for the system is less than 0.2, then in that case, if you look here, we have zeta square. So 0.2 is a small quantity. If we take a square of that, it would be more small. So actually the denominator would be approximately equal to 1. The under root of that one would be 1. So in that cases, we could use equation that is 1 by n natural log x1 by xn plus 1 is equal to approximately equal to 2 pi zeta. And it, you could see also this here, this actually in this plot, this is the simulation of these two equations. This is the logarithmic decrement, that is natural log of x1 by x2, which has been taken along the vertical, whereas along the horizontal axis, zeta, which is c by cc, actual damping to the critical damping, it is taken. So the full line or the dark line is actually the simulation or plot of this equation, whereas the dotted line represents the simulation of this equation 2 pi zeta. If you look at the plot of the first equation, that is this one, we could easily see that here somewhat the plot is linear. Here the plot is linear, and if we up to, it is linear up to 0.2. So both of the models are actually coinciding over each other. So you would get the same values from both of the models up to 0.2. We would get the same value from both of the plots up to 0.2. So we could say that if the damping ratio is less than 0.2, then in that case we could use the simplified equation, that is 2 pi zeta. If we don't know that what would be the range for the damping ratio, then it is more actually desirable to use this equation or this mathematical model. Now here you could see an example to find out the damping ratio from the experimental plot. Let's say we have this experimental plot. So here what you have to take, first you have to select the amplitude. So I'm taking this line. Let's say this is point 1, and you have to choose a number of cycles, and let's say I'm choosing 5 cycles. So one cycle from here, if we move, so this is cycle number 1, 2, 3, 4, 5. So we are choosing 5 cycles. So this is point 1, so we have x1, and this is point xn plus 1, that is after n cycles. So n is 5. We have chosen n as 5. So we n plus 1, 6. So x6. So what you have to do, you have to just measure the amplitude x1 and the amplitude x6 from the experimental plot. So let's say we are measuring it. X1 is, let's say, equal to 0.68, and x6 is 0.12, and then we have 1 over n. 1 over n here is 5 natural log of x1 by x6, and we are using the second equation, which is approximately equal to 2 pi zeta. The only unknown is zeta, and from there zeta is actually equal to 0.055 or 5.5%. So using logarithmic method, very easily we could find out the damping ratio for the underdamped systems. But for that, what you need, you need the plot. You need the plot when the system has been subjected to the free vibration. So once we have that experimental plot, so very easily using that method you could find out zeta. The next topic that we would be discussing, it is a very important topic, and that topic is actually the effect of including the mass of the spring and the value of the natural frequency. Actually, when we are doing modeling, we are doing a number of assumptions, but valid assumptions. If you are doing valid assumption, then in that case, actually the error in your modeling would be less. But if we are not doing a valid assumption, if it is not actually following, it means that you are not following the physics. So in that case, actually the modeling would be incorrect, and the when you at the end you calculate your answers, then there would be tremendous amount of error in that. So actually, when we are modeling the systems, so actually sometimes depending upon that mass which is suspended through the spring, we if the mass is suspended, if the mass which is suspended through the spring, it is too much than the mass of the spring, so in that case we could ignore the mass of the spring. For example, in case of automobile, the mass of the automobile is 1 ton, that is 1000 kilogram, 2000 kilogram, 4000 kilogram, 5000 kilogram, depending upon the type and size of the automobile. But a small passenger vehicle is actually around about 1000 kilogram. If we look at the mass of the suspension spring, so in comparison, the mass of the suspension spring would be half kilogram. So in that case, on one side we have 1000, 2000, 3000 kilograms, whereas on the other side the mass of the spring is half kilogram. So in that case, our valid assumption would be, if we ignore the mass of the spring in that case, then actually the analysis would become easy, the modeling would become easy, but the disadvantage would be there would be slight error. There would be an error of 2%. 2 to 10%, but 2 to 10% error is actually acceptable. But on the other hand, if we have a cantilever beam and on the beam there is a mass of 1 kilogram, at the tip of the beam we have 1 kilogram mass, and the mass of the beam itself is half kilogram. So in that case, if we ignore the mass of the beam, then actually um, our modeling would have error. At the end, if you do the calculation, if you find the natural frequency, if you find the response of the system, and you compare with the experimental results, then there would be a tremendous amount of error. So in all those cases where actually the mass of the spring is considerable, so we have to consider it. And this topic is about that. So the effect of including the mass of the spring on the value of the natural frequency. So let's say that we have a mass, it is suspended through a spring, and the spring has also the considerable mass. Uh, let's say it is ms. Ms is the mass of the spring, k is the stiffness of the spring. So in order to come up with the mathematical model where we could include also the effect of the mass of the spring, we have to do some derivation. So let's say for the derivation, we know that this mass would be moving, let's say it is moving in this direction, and at this instant it is moving in this direction, and the displacement is x of t. The length of the spring, unstretched spring, or the spring at this instant, let's say it is L. And I am taking this small portion of the spring, infinitesimal small portion of the spring, and let's say the length of this small portion of the spring is dy. Its mass is dm. And this end of this small portion of the spring from the support, let's say it is y. So this displacement up to the other end of the small infinitesimal portion of the spring would be y plus dy, and this distance is y. So we would be using Rayleigh's method. And in the Rayleigh's method, you could use the Rayleigh's method for conservative system, for those systems where there is no damping. So here you could see that we have just a spring mass system. So we could use Rayleigh's method. Rayleigh's method states that the maximum kinetic energy of the system must be equal to the maximum potential energy. So we need to come up with the equation for the maximum kinetic energy and the equation for the maximum potential energy. But here the potential energy would be stored in the spring in the form of strain energy. So we have to find out the strain energy of the spring. Kinetic energy, here we have two masses. One is the mass, the lumped mass, which is suspended through the spring. So it would have a kinetic energy, and the other, as the spring has mass, so it would have also kinetic energy. So the total kinetic energy of the system would be kinetic energy of spring plus kinetic energy of the mass. So in order to find out the kinetic energy, the total kinetic energy, that is the kinetic energy of this mass, in order to find the kinetic energy of this mass, that is very easy, because we know the equation for the kinetic energy is half mv square. Here we have mass, so the kinetic energy of the mass is equal to half m, and x of t is the displacement, so x dot would be the velocity, so the kinetic energy of the mass would be half mx dot square. Next we have to find out the kinetic energy of the spring. So the kinetic energy of the spring, finding the kinetic energy of the spring is a little bit tricky. So because we have taken a small portion of the spring, and that small portion of the spring has mass, um, let's say dms, and the mass of the element of the spring dy is actually equal to ms by L dy. How we got that equation? That derivation is done here. Let's say mass of L is the length of the spring. Mass of length L of the spring is equal to ms, the total mass of the spring. And if we divide the equation on both sides by L, so here we would have 1. So this is the mass of the unit length of the spring. So mass of the unit length of the spring would be ms by L. We are actually we want to find out the mass of uh, uh, size dy of the spring, the mass of the differential element dy of the spring. So multiplying now the equation on both sides by dy. So if we multiply here by dy, so we would have dy. So mass of dy length of the spring is equal to ms times dy by L. So we would get this equation. So mass of the differential element dy of the spring is actually equal to ms by L times dy. Similarly, we have to find out the velocity of this mass, velocity of this mass. If you look here, we are taking this mass, the it is connected here, it is connected here. The length of this portion of the string through which this small mass is suspended, it is y. So velocity of the element of spring dy, it is equal to v subscript dy is equal to y by L x dot of t. And how we got this equation? Derivation is done here. So velocity of spring at L length is equal to x dot. If we move from here, what is the spring length here? 0. If we move in the downward direction, that is y. This is y. In the downward direction, this is y. The y is increasing. And when we reach here, this is the length of the spring. So when y is actually, this is y, when y is actually equal to L, when y is actually equal to L, then how much is the velocity? Velocity at this end of the spring is x of t. So velocity at L length of spring is equal to x dot. Dividing the equation throughout by L, velocity at one length, that is unit length of the spring, is equal to x dot by L. Velocity at y, multiplying, because we want to find out the velocity of this portion of the mass. So at distance y, length of the spring, the velocity would be x dot times y by L. So velocity of the differential element of spring dy, it would be y by L x dot. So now we have actually the velocity for the differential element of spring. We have the mass of the differential element of the spring. So kinetic energy of the uh, differential element of spring, that is dm, it is equal to half mass here, it is dm, and the velocity of that small mass is v subscript dy whole square. So this is the kinetic energy. So putting for small mass dm, which is ms by L dy, and putting for the velocity, which is y by L x dot whole square. So this is actually the kinetic energy of this small portion of the spring. And in order to find out the kinetic energy of the whole spring, we have to integrate. We have to integrate this equation. And we have to integrate from 0 to length L. So here the length of the spring is 0, and here the length of the spring is L. So we have to integrate from 0 to L. So the kinetic energy of the spring, so integrating this equation, 1 by 2 is constant. So writing it out of the sign of integration, integral sign 0 to L, ms by L, ms by L, this is ms by L, dy, we are writing this dy here, and then we have y by Lx dot whole square. So ms by L is constant, so writing this out of the sign of integral, and here we would have x dot. X dot is the velocity of this mass. It is also constant, so we could also write this out of the sign of integration, and we have y by L. And if we integrate this, we would have uh, here we have y square, and if we integrate that, so we would have y cube by 3. And when we apply the limits, then we would have L cube, by L square, and one L would cancel with that one, and this L would cancel with that L, and after simplification we would have the kinetic energy of spring as 1 by 2 ms by 3 x dot square. So this is the kinetic energy of the spring. So we have the kinetic energy of the mass, kinetic energy of the spring. Adding these two, we would have the total kinetic energy, and the total kinetic energy would be half, which is the kinetic energy of the spring, kinetic energy of the mass, and the maximum kinetic energy, the amplitude. You have to put the amplitude for the velocity, and the amplitude for the velocity is omega n square a n square. So this is the maximum kinetic energy for the system, and the maximum and the potential energy is actually stored in the spring as strain energy, and it is half kx square, and maximum potential energy is actually at the extreme position, so it is half k a square. X, instead of x we have to put the amplitude a square. So now we have the equation for the maximum kinetic energy, equation for the maximum potential energy. We have to equate these two using the Rayleigh's method. So this 1 by 2 would cancel with this 1 by 2. A square would cancel with a square, and at the end we would have m plus ms by 3 times omega n square is equal to k. And bringing this term on the other side of the equation, we would have omega n square is equal to k by m plus ms by 3. And taking square root on both sides, we would have omega n is equal to under the root k by m plus ms by 3. So now we got the model for the systems where the spring mass is considerable. It is not ignorable. The spring mass is actually comparable to the mass of the suspended mass of the system. So in that case, we have to use this mathematical model. Omega n is equal to under the root k by m plus ms by 3. In all other cases where the suspended mass is actually too much, then the mass of the spring, then in all those cases we could ignore that. And you could also see that in the equation. If this quantity is a small quantity in comparison to m, if ms is a small quantity in comparison to m, and if we divide a small quantity by 3, it will become more small. It would become more small. And in that case, the effect of this on the mass would be ignorable or less. So using the modeling, next we would be in the position to solve a very interesting example. The statement is effect of fuel on frequency of an airplane wing. So let's say we have a fighter aircraft. If we have a fighter aircraft, and we want to find out the natural frequency of the wing of the fighter aircraft. Experimentally, it is not an easy task. The beauty of the modeling is that actually we would be not conducting any experiment. Just by using the mathematical models which we have developed, we would use those mathematical models, and very simply within 1 minute we would come with the answer. We would need some data. We would need some data for the calculation, and you could very simply ask those, or you could find those data on the internet, or you could get those uh, that data from the catalogs of the instruments or machines. So that is actually not the problem. So very complicated problem, a continuous system, a real system, and we want to find out its natural frequency with very ease with the help of the modeling. So let's say that we have a fighter aircraft. The mass of the pod is 10 kilogram when it is empty. Let's say this is the pod, and when it is empty, there is no fuel in that pod. Its mass is 10 kilogram, and when it is full of fuel, its mass is 1000 kilogram. I is the second moment of area of the wing. The second moment of area of the wing is I. It is 5.2 into 10 raised to the power minus 4 meter 4. Young's modulus of the material of this wing, which is actually in most of the cases, it is a structured steel and actually aluminum alloy. So E is 6.9 into 10 raised to the power 9 Newton per meter. And length of the wing is actually, let's say, 2 meters. So that information is available, and using that information we have to compute the natural frequency of the wing and the effect of the fuel on the natural frequency of the wing. So first, what do we have to do? We have to look at our system, and then we have to model it. First, we have to perform modeling. So we could model this wing as a cantilever wing. If you look here, this wing is actually attached to the body of the aircraft, but this end of the wing is free, and there is some mass. So we could actually model this as a cantilever beam. So modeling this as a cantilever beam, this is a fixed support, and this end of the beam is fixed to the support, whereas the other end is free and there is mass. And let's say that mass is m. E is the Young's modulus of the material of the cantilever. I is the second moment of area of the beam, and L is the length of the beam. And let's say x of t is the response of this cantilever beam. So the first step is you have to model your system, and we are ignoring the damping. So in that case, our system would be an undamped system, and we want to find out its natural frequency. That is the, and we are modeling this as a 1 degree of freedom system. We have one spring and one mass. So we are modeling this as a 1 degree of freedom system. So it would have one natural frequency. When we model this as a 1 degree of freedom system, we would get the first frequency of the airplane wing, which would be the fundamental frequency. Omega n, as we studied in our previous lectures, for 1 degree of freedom system, the circular natural frequency is actually equal to under the root k by n, the undamped natural frequency. And the frequency Fn would be 1 over 2 pi omega n. K, actually now we have a cantilever beam, and for the cantilever beam we have already developed a model for the stiffness. Beam stiffness is 3 EI by L cube. So we have the model for the stiffness of the cantilever beam. So first, model wing as transverse beam, that is cantilever beam. Model fuel as tip mass. So we are modeling the fuel as tip mass. Ignore the mass of the wing, and so see how the frequency of the system changes as the fuel is used up. So we are ignoring the mass of the wing, although this is a valid assumption, because in comparison to 1000 kilogram of the fuel, the mass of the wing would be not too much, but still it would actually put error in your calculation. So We have the model omega full, that is when the pod is full of fuel. The model for the natural frequency of the cantilever beam 3 EI by ml cube. E is given, I is given, that is known, and length is known. And when the pod is full, it is 1000 kilogram. So after putting that and after calculation, the answer is 11.6 radians per second. So circular natural frequency is 11.6 radians per second and frequency is 1.8 hertz. And when the pod is empty, instead of 1000, we have to put 10 kilograms. So here we are putting 10 kilograms, and then after computation, omega empty is equal to 115 radians per second and 18.5 hertz. So you could see that when actually the aircraft is consuming the fuel, so with the passage of time, the mass of the pod, as the pod is getting empty, the mass of the pod would be decreasing. On the other hand, the natural frequency of the wing would increase, and it is in this case it would increase from 1.8 hertz to 18.5 hertz. So theoretically, we could very easily we have calculated the natural frequency of the wing, which actually depends upon the mass of the fuel, and it actually ranges from 1.8 hertz to 18.5 hertz. And this is actually the beauty of the modeling and analysis, that very easy for a very complicated system, real system, continuous system, very easily we have actually found out the natural frequency. Although there would be error if we do the experimentation on the real aircraft wing, um, the we would get frequency, but that frequency would be close to actually the calculated one. In other words, the calculated one would be very close to the experimental frequency. If the experimental frequency would be 1.9 hertz, 9 hertz or 2 hertz, our theoretical is 1.8 hertz. The error would be from 2 to 10%, but that error is acceptable for the ease with which we have done the calculation. If we find out the actual frequency or the experimental frequency, in this case it would be 20 hertz, and when we do the calculation using the modeling, the answer is, let's say, 18.5 hertz. The error is 2 to 10%. It is acceptable for the ease with which you are doing the calculation or computation. Thank you.